All right, so this is 14.7a, video number 3. I'm hoping that I can keep this one to about 25 minutes, but these problems do take a long time, so let's get rolling. Find the absolute maximum, the minimum values of f on the set D if f of x is defined there. Let's see, our domain looks like it's x goes from 0 to 3, y goes from 0 to 2. So let's sketch the domain. So let's see here, we're going to have x goes from 0 to 3, and y goes from 0 to 2. So that's 3, that's 2. Yeah, that looks about right. Okay. So we know we're going to have to find critical values. So fx is going to be 4x cubed minus 4y. Fy is going to be 4y cubed minus 4x. We've got to set each one equal to 0. Let's see, we can divide the 4's out of everything, which is nice. So really what we get here is that x cubed equals y. So if I were to go ahead and plug x cubed into the y over here in fy, we're going to get x cubed minus x equals 0. So it's really x to the 9th minus x equals 0. Factor in x, you get x to the 8th minus 1. So we're either going to get that x equals 0 or x equals plus or minus 1. So we can plug these things back in. If x equals 0, plug those back in. Oops, not for y. Plug them back in over here. If x equals 0, y equals 0. So I have a critical point at 0, 0. If x equals 1, y equals 1. So I have a critical point at 1, 1. And if x equals negative 1, that's outside of our domain. So we don't have to worry about the negative part. So the negative part is out because it's not in our domain. So we've got two critical values. Plugging each one of those back into the original function. If I plug in 0, 0, we get 2. We plug in 1, 1, you get 1 plus 1, which is 2, minus 4 plus 2, so we get 0. So we have our critical points. Let's go ahead and do the endpoints. We didn't do it that way last time, so I'll switch it up. Let's do the endpoints. Got 4 endpoints. I've already done 0, 0. That's nice. I don't have to do that one again, but I'll write it down anyway just to make sure. So I've got endpoints at 0, 0, which we already know is 2. I've got another endpoint at 3, 0. I've got an endpoint at 3, 2. And I have an endpoint at 0, 2. So if we plug in 3, 0, there's going to be some big numbers. Let's see. 3 to the 4th power is 81. Oh, that's not so bad because the 0 for y makes those two things go away. So you get 81 plus 2 is 83. That's definitely the leader in the clubhouse for the max. Plugging in, let's do 0, 2 first. It'll be easier. So if I put 0 in for x, the only thing I have to do left is the 2 to the 4th power plus 2. So that's 16 plus 2 is 18. Okay, that's definitely not the max, and it's not the min. And 3, 2. Let's see. If I plug in 3, I'm going to get 81. 2 for the y's is going to give me 16. So 81 and 16 is 97. Minus 4 times 3 times 2. So it's what, 12, 24. So 97 minus 24 is 73 plus 2 more 75. So not the max, not the min. Now we have to go with our lines. And again, it doesn't matter where you start. I'm going to call this one L1 this time, then L2, then L3, then L4. So let's go ahead and figure these things out. So along L1, that is the y-axis, which is the equation x equals 0. Which means that my function will be a function of x equaling 0, comma y. Well, that's just going to be y to the fourth plus 2. We take the derivative of 0y, which is going to be 4y cubed. Set that equal to 0. Y has to be 0. If y is 0, plugging that back in, excuse me, now we have x is 0, y is 0. We've already done that. That's at the point 0, 0, which we already know is 2. Let's do this along L2. That's the x-axis, so that's y equals 0. So if I do y equals 0, that's going to be the function of x comma 0. And that's going to be x to the fourth plus 2. Okay, taking the derivative of that one is going to be 4x cubed. Setting that equal to 0 means that x equals 0. So once again, we have the point 0, 0, which again we know is 2. L3 is going to be the equation x equals 3. So now I'm going to do the function of 3 comma y. This is going to be a little bit different because I actually have to plug some stuff in here. So plugging in a 3 is going to give me 81 plus y to the fourth. 81 plus y to the fourth minus 12y plus 2. Minus 12y plus 2. So your derivative, the constants will go to 0, so you get 4y cubed minus 12 equals 0. So we actually will have something here. So adding 12 and dividing by 4, you get that y cubed equals 3, or y equals the cube root of 3. So that means we have the point 3 cube root of 3, which we have to plug back in. Okay, not exactly an easy one to do here. If you use your calculator on this one, you're going to get approximately 70 point something, but that's nowhere near the maximum, so we're good. We don't really have to know the exact value there. And then L4 is going to be along the equation y equals 2. So that would be x comma 2, which plugging that one back in actually gives you x to the fourth plus 16 minus 8x plus 2. So taking the derivative of that one is going to be 4x cubed minus 8 equals 0. Add the 8 and divide by 4, you get that x cubed equals 2. So now x would be the cube root of 2. And then if you were to plug in, let's see, what's that going to be? Cube root of 2 comma 2. Again, you plug that in, you get 10 point something. Not the max, not the min. So then we just go back up and find all of our values. So the highest value was definitely, 83. And the lowest value here looks like it was 0. So our absolute max was 3083. And the absolute min occurred at 110. All right, I'll be lucky to keep this under 30 minutes. We'll see. Find the absolute max and absolute min values of f on the set D, where D this time is defined as a triangular region. So this one's definitely a little bit different. With the vertices of the triangular region at 0, 0, 5, 0, and 1 comma 4. We'll call that about 4, 1 comma 4. We'll say that that's 1. So this is our triangular region here for our domain. So that one's definitely going to be interesting. So I'm going to label that one L1, L2, and L3. L2 and L3, we're going to have to do a little bit of work on to find. But let's start off with the other stuff. Let's start off with critical values. So fx is going to be 4. Well, the nice thing about that is that can never equal 0. Fy is -5, which can also never equal 0. So there's no critical points. No interior critical points here because our partials can't give us any. Let's do the endpoints. So those are the easier things to do here. So our endpoints are going to be at the point 0, 0, 5, 0, and 1, 4. Kind of given to us there. So at 0, 0, plugging that in, we get 1. Plugging in 5, 0, you're going to get 1 plus 20 minus 0, so it's 21. And then plugging in 1, 4. So you're going to get 1 plus 4 minus 20. So 5 minus 20, -15. So it looks like at the point 1, 4, this thing dips down pretty far. Now, whether that's the absolute minimum or not, we'll have to find out. So we've got to do our borders. The first line is the one that's on the x-axis, so that's y equals 0. So that means we're going to have a function of x comma 0. And the function of x0 is going to be 1 plus 4x. If I take the derivative of that, we get 4. Well, that can never equal 0. So there's no critical values along that line. Let's do the second line. Now we have to do a little bit of work. L2 is this one right here. Well, that is definitely not an easier one. You have to kind of figure out what the equation of that line is. Well, that's going to be along the line y equals, let's see if we can figure this out. I've got 2 points, so I can find the slope between the 2 points. Between the point 5, 0 and 1, 4, the slope is -1, I believe. Let's see, is that right? Down 1, right? Yeah, down 1, right 1, so it's -1. And if that's the case, if I had gone up 1, left 1, that means it would have had a y-intercept there. So it looks like this is y equals -x plus 5. So basically, it's just knowing how to write the equation of a line. You have 2 points, you can write the equation of a line. You can do it in point-slope form, you can do it in slope-intercept form, whatever's easiest for you. Probably slope-intercept form because that gives us a way to substitute something in for y. So what that gives us is the function. The function is going to be a function of x comma y, but y is -x plus 5. So that means for every y value up here, I'm going to plug in -x plus 5. So we get 1 plus 4x minus 5 times -x plus 5. Now, if you really want to go ahead and work this whole thing out, you can. But once you distribute this, you're going to get a -5 times the -x, which is a 5x, which you'll add to your 4x, will give you 9x. When you take the derivative here is going to be a constant. So f prime of this, it's going to equal 9, but it's going to be a constant. And the constant, as long as that constant is not 0, cannot be 0. So again, there's no critical values along that specific linear piece. And then L3 is going to be this equation right here, which looks like it is a slope of, what is that, up 4, right 1. So slope of 4, y-intercept of 0. So it's y equals 4x. So that means we're going to have a function of x comma 4x, which if we plug that back in, we're going to get 1 plus 4x minus 20x. Which, once again, if you go ahead and combine that, you get -16x. You're going to get -16 for your derivative. So in this case, you get -16, which cannot equal 0. So there really are no critical values along that line, but you still have to test all those boundaries just to see. So really, we have all of our values. We had no critical values, and we had no critical values along the boundaries. So really it was at the endpoints. Makes it pretty easy that this is your max, that one's your min. So we can say that our, oops, it's supposed to be in red. Come on, work for me here. Absolute max is at the point 5, 0, 21, and the absolute min is at the point 1, 4, negative 15. All right, one more to go. Again, it's a longer one, but hopefully you'll see why this one's important. Find the absolute max and min values of f on the set D if f of x is defined there, and the domain is x squared plus y squared is less than or equal to 1. Why that's important is because it is a circle. So I am looking at a domain inside and including the boundary of that. Well, this is a circle where the radius is 1. All right, so that's kind of an important factor. We're going to have to go back to some trig on this one. So the first thing we can do is we can still do our critical values. We can still do that part. Fx is going to be 6x squared. Setting that equal to 0 gives us x equals 0. Fy is going to be 4y cubed. Setting that equal to 0 gives us y equals 0. So we know we have a critical point at 0, 0. Plugging that in, you also get a value of 0. All right, so there's one of them. Now, in order to do the boundary, well, the boundary is comprised of the circle x squared plus y squared is less than or equal to 1. In order to do this, it's probably going to be best to change this into polar. All right, and why might you need to change this into polar? Well, what you have to consider is that this thing could be waving up and down. It's really hard to draw this, but it could be doing like this all the way around the circle or something like that. It could be going up and down. It's a horrible drawing there. But it could be definitely waving up and down. Remember, we're just seeing the projection down into the two-dimensional plane here for this thing. So there are going to be several possible angles that could give us the measurement here. Finding this in terms of a Cartesian plane or an XY rectangular coordinate plane probably won't be as easy to do. So let's put it into polar. So we have to remember, in polar, x equals r cosine theta and y equals r sine theta. Okay, those are your two polar conversions. So if we're going to do a function of x, well, in this case, r equals 1, so it makes it a little bit easier. So when I plug the 1 in, we're just going to get that x is cosine theta, y is sine theta. Well, that means we're going to have to plug cosine theta in for each x, which is there. So we're going to get 2 cosine cubed of theta plus plugging sine theta in for y, we get sine to the 4th of theta. Well, now I really don't have multiple variables anymore. I've just got one variable, so I can just take a derivative. I'm going to take the derivative of the function of cosine theta sine theta. Well, it is going to follow some chain rule type stuff. So with the first one, 2 cosine cubed is going to be bring the 3 out to the front, multiply it, reduce the power by 1, chain rule multiplied by the derivative of cosine, which is negative sine, plus, similar idea for sine, bring the 4 out front, reduce the power by 1, multiplied by the derivative of sine, which is cosine, and all that has to be equal to 0. So let's see how we can simplify this thing a little bit. Looks like I can factor out a sine and a cosine and a 2, or maybe even a negative 2. Let's factor a negative 2 out and see how that works. Doesn't really matter if we factor the negative out or not. So it looks like I can factor out a -2, a sine theta, and a cosine theta from each one. So that's going to make this 3. Take the sine theta away, take one of the cosines. So 3 cosine theta. Take one of the cosines away from the second one. That will become a -2 now. And take away one of the sines. So that's going to be sine squared. Yeah, theta equals 0. So -2 cosine theta sine theta. Actually, if you recognize that, that is the double angle of sine theta, just the negative of it. So that's actually kind of nice. So I can set that, sorry, that'll be, yeah, negative sine of 2 theta equals 0, or 3 cosine theta minus 2 sine squared theta has to equal 0. All right. In the one on the right, we're going to have to do a little work because I need to change everything into terms of cosine in order for me to be able to factor it. So 3 cosine theta minus 2 times sine squared is 1 minus cosine squared theta. Let's see, a little distribution there. We're going to get 2 cosine theta, excuse me, cosine squared theta plus 3 cosine theta minus 2 equals 0. And then that does factor. That'll be 2 cosine theta there. It's going to have to be a 2 and a 1. And it's going to have to be a positive and a negative. I believe that that's going to work. So from the first parentheses there, you get that cosine theta equals 1/2. From the second parentheses, you get cosine theta equals -2. Hopefully you all realize that that is extraneous because cosine will never equal -2. So that part doesn't even give us anything. So now we're ready to go ahead and solve this. So from this one, we know that theta is going to equal, let's see, cosine equals 1/2 at pi thirds and at 5 pi thirds. And we are just talking about one time around the circle because that's our domain, so we can stop there. Sine of 2 theta, you can get rid of the negative. We can divide the negative away from that. So we're just going to have that sine of 2 theta equals 0. Well, we know that sine is going to equal 0 at 0, pi, and 2 pi. But remember that that's 2 theta, which means I really have to go further around the circle, which means I've got to go to 3 pi and 4 pi. Because now when I solve for theta, dividing everything by 2, you get 0, pi halves, pi, 3 pi halves, and 2 pi. The good thing is 2 pi and 0 are going to be the same. So when it comes to testing, I don't need to worry about that. It's not that it's not part of it, but it's right back around to where 0 was. But this tells me I have 6 different values around the border that I need to check for absolute max and absolute min. So if theta equals 0, what's that going to correspond to? Well, if theta equals 0, that's really going to be the function of, remember our function was defined this way, cosine of 0 is 1, sine of 0 is 0. So that's a function of 1, 0. Come on. So if I plug 1 and 0 back into the original function, I'm going to get 2. Okay, we have to do this for all of them. So we're going to have to do this for pi halves, pi, 3 pi halves, pi thirds, and 5 pi thirds. Lots of values to do here. All right, so if we plug in pi halves, you're going to get a function of 0, 1. Plugging 0 and 1 back in, we are going to get 1. Okay, I'm going to try not to keep scrolling up and down here because that's wasting time. If you plug in pi, you're going to get negative 1, 0. And that is going to give you negative 2 when you plug it in. If you plug in 3 pi halves, you're going to get a function of 0 comma negative 1. Plugging that in gives you positive 1. If you plug in pi thirds, so cosine of pi thirds is a half, sine is root 3 over 2. Plugging that in, you actually end up with 13/16, which is less than 1, but still not as low as negative 2. And then if you plug in 5 pi thirds, you're still going to get a half for cosine, but this time you're going to get negative root 3 over 2 for sine. But because I believe that that was being squared or raised, no? Oh yeah, to the fourth, sorry. It's still going to give you 13/16. It's the same thing. So, after all of that, the absolute maximum. What is the absolute maximum? So 2 looks like it's the biggest value here, and our critical point was way up the top at 0, so it's 2. So this one right here is going to be our absolute maximum, so that's going to be at the point 1, 0, 2. And the absolute minimum, it looks like negative 2, because I think that's the only negative value that we have, so that's going to be the point negative 1, 0, negative 2. A lot of work to be done on that one. But again, I think that was important to show, especially with converting that one to polar because of the fact that it was a circular domain. All right, plenty enough. There's 3 videos, very long videos, but these absolute max, absolute min problems, and even local max and local min problems take quite a bit of time.